Hello. So I'm continuing with the chapter coordination compounds. What did we study in the previous two classes? Recapitulating, we studied what are coordination compounds, definition and terminologies involved in those studies, Werner's theory of coordination compounds, and then ligands, different types of ligand, classification of ligands. Then after that, we discussed the formula of coordination compounds, what to be written inside the square bracket and what should be written outside. Then how to write the IUPAC names of different types of coordination compounds, namely cationic complexes, anionic complexes, coordination complexes, etc. Today, I would like to give you some more complexes, some more coordination compounds with their IUPAC names, so that you can be more familiar and it becomes easy for you to write the IUPAC names and how to arrange different groups which serve as ligands in the coordination compounds. After that, I will go to what's known as effective atomic number, and then the big part of it, isomerism, important, at the same time huge subchapter under coordination compounds. Okay, some more IUPAC names. Here I have written Hg, CO, CNS 6 times. This is an anionic complex. The counter ion is mercury. Suppose the counter ion is potassium, K4 FeCN6. You already know how to write the IUPAC name. This is potassium hexacyanidoferrate 2. But see, here potassium is enough because potassium has got the primary valency or the oxidation state of only +1 fixed. Whereas for mercury, the primary valency or the oxidation state vary. We have mercurous with +1 state, mercuric with +2 state. In such cases, even for the counter ions, we have to write the valency. So I have to write the valency for that. That's why I said I'm giving you some more compounds with IUPAC names. Therefore, this must be mercury. I have already told you the name should start with only small letter. Mercury, its oxidation state 2, the rest follows the anionic complexes. This is hexathiocyanate cobaltate, hexacyanido cobaltate 4. See the difference? Mercury 2. If it is potassium, sodium, etc., it is not necessary to write that. But for mercury, copper, you have to write that. So mercury 2 hexathiocyanato, this is thiocyanato, CNS. NCS is isothiocyanato. And I have already told you, for the anionic complexes, the central metal atom will end with the letters ATE. Okay? The next, NiCN4 2 minus. Here the oxidation state of nickel is 2. It's an anionic complex. Therefore, it must be, the IUPAC name should be tetracyanide nickelate 2 ion. Since it's an ion, you have to write that. Tetracyanide nickelate 2 ion. Okay, so second one is different from the first one. Third one is again different. In what way it is different? Why I have selected this for some more IUPAC names? Because NO2 is an ambidentate ligand. It can be present as this. We write this as nitro or nitrito N, or O double bond O minus. So this is minus. This is nitrito O. So it's an ambidentate ligand. Therefore, oxygen may be connected or nitrogen may be connected. That's why I have selected this complex for writing the IUPAC names. Here the counter ion is sodium. This is sodium. So sodium, suppose it is NO2, sodium hexanitrito N. So this is N is connected to cobalt. Otherwise we write ONO. Sodium hexanitrito N cobalt 3. So that is the name of the compound. I repeat, sodium hexanitrito N cobaltate 3. Cobaltate, anionic complex, cobaltate 3. Okay, next, K3FeCN5NO. Here NO, the oxidation state is 0, it is nitrosyl, because we have nitrosonium also, NO plus, but this is nitrosyl. Therefore, the IUPAC name of this compound is potassium pentacyanide nitrosyl ferrate 2. I repeat, potassium pentacyanide nitrosyl ferrate 2. Cyanide C should come first, nitrosyl N should come later. The next one, this is cationic complex. First find the oxidation state of iron. It is +2. This is oxalato ion or ligand. Therefore, the name of this compound is tetra aqua oxalato. Tetra aqua oxalato iron 2 sulfate. I repeat, tetra aqua oxalato iron 2 sulfate. The next one. So before you write the IUPAC name, first calculate the primary valency or calculate the oxidation state of the central metal. Okay, the next one. Tetra-aqua dichlorido chromium 3 ion. And this one, this is coordination complex having both cation and the anionic complexes. How to write this? If it is chromium and chromium, equal oxidation state must be distributed. But here this is -4 and this is -1. Totally it is 5. Then how to distribute between chromium and zinc? Will it be 2.5 and 2.5? Certainly no. Then how to write the IUPAC name of this? Here zinc has got the fixed oxidation state of +2. So zinc is +2. This is fixed. Therefore chromium must be 3, +3. Total it is -5, hence the positive charges should be +5. First fix zinc because it is fixed +2. Hence the name of this compound is pentaamine isothiocyanate chromium 3 tetrachlorido zincate 2. I repeat, pentaamine isothiocyanate chromium 3 tetrachlorido zincate 2, and that is the IUPAC name of the compound. Next, here is one heteroleptic complex. Again calculate the oxidation state. This is +3, which means this is -1, this is -1, this is -1. Therefore this is nitroso, so this is nitrito O, NO2. Hence the name of the compound is tetraamine chlorido nitrito O chromium 3 nitrate. So I repeat, tetraamine chlorido nitrito O chromium 3 nitrate. Okay. The next one, CO EN twice F2. This is ethylene diamine or ethane 1,2-diamine E, and this is fluorido, it is F. So E should come first, and this you should know the name of ClO4 counter ion. See, HClO4 is perchloric acid, KClO4 is potassium perchlorate. Therefore this ion is perchlorate. Perchlorate. Hence the name of the compound is bis. There are two ethylene diamine. Already in the word you have got ethylene diamine, therefore we cannot use di again. Therefore bis ethane 1,2-diamine difluorido cobalt 3 perchlorate. Okay, so I will write it, bis ethane 1,2-diamine fluorido cobalt 3 perchlorate. Perchlorate, that is the IUPAC name. And here you go back to this zinc and this. Here the central metal atom is platinum, here also it is platinum. The oxidation state of pyridyl group, pyridine, is 0, chloride is -4, therefore this -4 must be equally distributed between two platinum. In the previous 5 oxidation state, zinc is +2, we know, therefore it is chromium +3, that's how you decided. Now it is equal because both are platinum. Hence the IUPAC name of this is tetrapyridyl, this is tetrapyridyl platinum 2 tetrachlorido platinate 2. I repeat, tetrapyridyl platinum 2 tetrachlorido platinum 2 platinate 2. Then one more such complex, hexaamine chromium 3 trioxalato cobaltate 3. Okay, fine. Till now you haven't come across a compound of this type. These are called bridging coordination compounds, having bridging ligands. Here the ligands are amido NH2-, hydroxido OH-, and the counter ion sulfate and sulfate. Totally there are -6 oxidation state. Negative oxidation state is -3, -6. There are 2 central metal atom, cobalt and cobalt only, therefore it is equally distributed. It must be +3 and +3. First you should decide that one. Then you write EN twice bis ethane 1,2-diamine. Then cobalt 3. Fine. Then this is bridging. Such bridging ligand should be attached as the predecessor mu. So I repeat, bis ethane 1,2-diamine cobalt 3, mu amido, mu hydroxido, bis ethane 1,2-diamine cobalt 3 sulfate, the long name. Bis ethane 1,2-diamine cobalt 3, mu amido, mu hydroxido, cobalt 3, ethane 1,2-diamine cobalt 3 sulfate. Okay, fine. If that is the case, one Fe4 FeCN6 thrice, Fe4 FeCN6 thrice. Fe4 again, Fe has got the variable valency +2 and +3. Here it is +3, therefore this must be +2. Here it is +2 and this is +3. This is Fe4, that is ferric. Fe within present central metal atom is +2, therefore the name of this compound is iron 3. The name of this compound is iron 3. It should start with iron 3. Hexacyanido ferrate 2. Iron 3, hexacyanido ferrate 2. If outside it is 3 ferric, inside it is 2. If outside it is 2, inside it is 3. Now this is iron 2, this is ferrous, this is first one is ferric ferrocyanide, second one is ferrous ferricyanide. Therefore, this is reverse, iron 2 hexacyanidoferrate 3. So outside it is iron 2, this is hexacyanidoferrate 3. So outside it is ic, inside it is us, outside it is us, inside it is ic. Okay, so with this we shall stop the IUPAC names. We shall go to what is known as EAN. What is this EAN? Effective atomic number. Effective atomic number. You know that sodium combines with chlorine to give one electron. It becomes Na plus and Cl minus, because this becomes the electronic configuration of neon. This becomes 2, 8 and 8. It becomes argon. They attain the electronic configuration, 18 argon. They attain the electronic configuration. So every atom, while forming the compounds, whether it is covalent, coordinate or ionic, tries to attain the octet structure of the nearest noble gas atom. Even in coordination compounds, the central metal tries to attain the atomic number of the next noble gas by accepting the electrons from the ligands. The special thing about coordination compounds is the central metal accepts the electron from ligands. You know that metals are electropositive. They always give electrons to others. But in the case of coordination compounds, the central metal accepts the electron from the ligands. Ligands are Lewis bases. They donate electrons, and central metal acts as Lewis acid, accepting the electron. Okay, this is the speciality of the coordination compounds when compared to others. Right. See, EAN can be calculated by using the equation EAN is equal to Z minus X plus Y. What is this Z? Atomic number of the central metal. X, number of electrons lost to get the ion, the central metal ion. If no electrons are lost, X is 0. Y is the total number of electrons donated by all ligands. Donated by all ligands. Usually, this Z minus X plus Y approximately equal to the atomic number of the next noble gas. Next noble gas. Atomic number of the next noble gas. They try to attain the atomic number of the next noble. That's why metal accepts the electrons from the ligands. We shall try this with an example. Not only just one example, a few examples. K4 FeCN6. Atomic number of Fe is 26. Here it is present in +2 state. Fe2 plus, therefore, so Z is equal to 26, X is equal to 2, Y, there are 6 cyanide ligands, each cyanide will give a lone pair, totally 6 cyanide will give 6 into 2, 12, this is Y, therefore Z minus X plus Y is equal to 26 minus 2 plus 12, this is equal to 36. Krypton. 2 is helium, 10 is neon, 18 is argon, 36 is krypton. Thus, the central metal iron has attained the electronic configuration of the next noble gas, namely krypton. This is EAN. Now we shall calculate one or two more. K3 CuCN4. K3 CuCN4. Copper, atomic number 29, that is Z. Here copper is present as plus, therefore X is equal to 1. There are 4 cyanides, therefore 4 into 2 is equal to 8, that is equal to Y. Therefore EAN is equal to 29 minus 1 plus 8, again 36, electronic configuration or atomic number of krypton. Next, NiCO 4 times. Ni atomic number Z is equal to 28. Here X is equal to 0 because oxidation state of nickel is 0. It is present in the form of an central metal atom. Y, there are 4 ligands, each will give 2. 4 into 2 is equal to 8. Therefore 28 minus 0 plus 8, again 36. Copper, around it, after the formation of coordination compounds, will have 36 electrons, similar to krypton. But there are a few exceptions to this, very few, but they try to attain the electronic configuration of the next noble gas. See here, Cu NH3 4 times SO4. Cu NH3 4 times SO4. Cu, Z for Cu is 29. Here Cu is present as +2 state, therefore X is equal to 2. There are 4 ammonia ligands. 4 ammonia ligands will give 4 into 2, 8. That is equal to Y. Therefore EAN is equal to Z minus X plus Y. It comes to 35, nearer to krypton, not equal to that. So this is about EAN. They try to attain the electronic configuration of the next noble gas. This is about the purpose of accepting the electron from the ligands by the central atom is to attain the electronic configuration of the next noble gas atom. Okay, right. This is EAN. Z minus X plus Y. Then the next one, isomerism. You know that isomerism is compounds having the same molecular formula with different structures or different types of arrangement in 3 dimensions. That is isomerism. Isomerism is broadly classified into 2. You already know this: structural isomerism and stereoisomerism. Isomerism is broadly classified into 2, structural and stereo, which you already know under organic chemistry. But here, the structural isomerism, under structural isomerism, you don't have position, chain, functional, metamerism, tautomerism. No. Instead of that, you have ionization isomerism, you have what is known as hydrate isomerism or solvate isomerism, you have linkage isomerism, and you have coordination isomerism. Coordination isomerism. So under structural, I repeat, isomerism is compounds, coordination compounds having the same molecular formula but having different structures or different in the distribution of ligands in space, 3 dimension. According to that, we have structural isomerism and stereoisomerism. Under structural isomerism, we have ionization isomerism, hydrate or solvate isomerism, linkage isomerism, coordination isomerism. And then under stereoisomerism, we have geometric isomerism, same as geometrical isomerism, and optical isomerism, same as organic compounds. Now we shall see this isomerism one by one. First one, ionization isomerism. Ionization isomerism. What do you mean by this ionization isomerism? 2 coordination compounds will have the same formula, same number of atoms, same coordination number, same central metal atom, same central metal ion. But if you dissolve this in water, you dissolve this in water, it gives different ions. Therefore, it's called ionization isomerism. So, you can distinguish the 2 isomers by knowing which are the ions that are formed in the aqueous solution. How to test that? You can test those ions just like the basic radicals which you have tested in the laboratory. I'll give you an example for ionization isomerism. CO NH3 5 times Br SO4. For this we can write one more formula, CO NH3 5 times SO4 Br. You see here, both have the same molecular formula, but counter ions are different. Counter ion here is sulfate, the counter ion is bromide. Therefore, if you dissolve this in water, you get sulfate ion and this cation CH3 5 times Br 2 plus. How do you know that sulfate ion is obtained? Add barium chloride to it, you get a white precipitate of barium sulfate. Confirmed. You dissolve this in water, you get the cation, the complex ion NH3 5 times SO4 plus and Br minus. How do you confirm that Br minus is obtained as the counter ion? Add silver nitrate solution, you get a pale yellow precipitate of silver bromide which is sparingly soluble in ammonium hydroxide. Thus, this is an example for ionization isomerism. You can confirm it by testing by adding barium sulfate to the first one and silver nitrate to the second one. I'll give you a few more. PT NH3 4 times Cl2 Br2. PT, it's all right. PT NH3 4 times Br2 Cl2. See here, the counter ion is Br, counter ion is chloride. So if you dissolve this in water, you get the complex ion and bromide. If you dissolve this in water, you get the complex ion and 2Cl minus. Add silver nitrate to the aqueous solution, you find pale yellow precipitate of AgBr sparingly soluble in ammonium hydroxide. If you add AgNO3 here, you get a white curdy white precipitate of AgCl. This is AgBr sparingly soluble in ammonium hydroxide. This is AgCl soluble in ammonium hydroxide. This is how the ionization isomerism works, or you can find out the ionization isomerism. So one more example, I will stop there about ionization isomerism. CO NH3 4 times Cl2 NO2. Another is CO NH3 4 times Cl NO2 Cl. If you dissolve this in water, you get nitrite ion. You can test it by adding dilute HCl and ferrous sulfate. You get brown color. If you dissolve it in water, you get Cl minus. Add AgNO3 white precipitate soluble in ammonium hydroxide. Thus, ionization isomerism is compounds having the same molecular formula but differing in the ions that are formed when it is dissolved in water. This is ionization isomerism. Second one is hydrate isomerism or solvate isomerism. Here, different coordination compounds will have the same molecular formula, but number of water molecules present as the ligand and present along with the counter ion are different. I'll explain that. Then only you will appreciate this type of isomerism. H2O 6 times Cl3. The name of this compound is hexaaqua chromium 3 chloride. This will exhibit this hydrate or solvate isomerism. The second structure possible is H2O 5 times Cl, Cl2, H2O. Third one, H2O 4 times Cl2, Cl2H2O. You can see here, three structures are possible. First, hexaaqua chromium 3 chloride. Second one, pentaaqua chlorido chromium 3 chloride monohydrate. Third one, tetraaqua dichlorido chromium 3 chloride dihydrate. How do you know that these structures exist? You add AgNO3 to this, you get 3 moles of AgCl, which shows that 3 chloride ions are present as counter ions. To this, if you add AgNO3, you get 2 AgCl, showing out of 3, only 2 are present as counter ions, 1 acts as a ligand. So, the place of one H2O and 1 chloride has been exchanged. 1 H2O comes out of the coordination sphere, 1 chlorine enters into the coordination sphere. This one, if you add AgNO3, of course in the aqueous solution, you get 1 mole of AgCl, showing that only 1 chloride is present as the counter ion. So 2 molecules of water present as ligand come out as dihydrate, and 2 chlorine, which was present as a counter ion, enters as the ligand. Werner was not able to explain this theory or this part. What is that part? Chlorine can satisfy the primary valency as well as the secondary valency. Here it satisfies primary, here it satisfies in the second and third, it satisfies both primary and the secondary valency. And that was the limitation of Werner's theory, but today we know those details. This is hydrate or solvate isomerism. We can give any number of examples for this. I would like to give just one example for this. One more example. CO NH3 4 times H2O Cl Br2. Cl Br2. This CO NH3 4 times Br2 Cl H2O. You can see here, it's a hydrate. H2O was a ligand here, now H2O is outside the coordination sphere. Bromide was the counter ion, now Br2 has become the ligand, exchange of H2O with that. So that's about the solvate isomerism. So I explained the hydrate isomerism or solvate isomerism. I explained ionization isomerism. We shall go to linkage isomerism. I will take another 2 or 3 minutes. Linkage isomerism. You already know that nitrito N has got the lone pair, O has got the lone pair, CN, C can be connected to the central metal or N can be connected to the central metal. CNS, C can be connected to the central metal atom, or NCS, N can be connected. CNO, C can be connected to the central metal, it's the ligand, it is the ligating atom. NCO, same groups. Nitro connected to N, nitro connected to O, etc. These are called ambidentate ligands. Ambidentate ligands. If the compound has got ambidentate ligands, depending whether N is connected or O is connected or carbon is connected or N is connected, we will have different coordination complexes with the different names. This is called linkage isomerism. So I'll give you 1 or 2 examples for linkage isomerism. CO, NH3 5 times, NO2, Cl2, CO, NH3 5 times, ONO, Cl2. Here N is the ligating atom, N is connected to the central metal atom cobalt. Here O is connected to the cobalt. Therefore the names of the compounds are pentaamine nitrito N cobalt 3 chloride. This is -1, this is -2, therefore this is +3. Same thing will apply here. So N is connected, therefore we call it pentaamine nitrito N cobalt 3 chloride. Whereas here pentaamine nitrito O is connected to the central metal, O is the ligating atom. Therefore the name is pentaamine nitrito O cobalt 3 chloride. That doesn't change, +3 doesn't change. So this is pentaamine nitrito N cobalt 3 chloride. This is pentaamine nitrito O cobalt 3 chloride. Okay, the last one under structural isomerism, coordinate. So in this way you can write any number of examples for this. If you have ambidentate ligands, you find that linkage isomerism. For example, palladium, Py stands for pyridine or pyridyl, CNS twice is the ambidentate ligand. Palladium dipyridyl, NCS twice. This is thiocyaneto, this is isothiocyaneto. So this is dipyridyl dithiocyaneto palladium 2, whereas this one is dipyridyl diisothiocyaneto palladium 2. So this is about. The last one I will explain in 1 minute, that is coordination isomerism. Coordination complexes exhibit this type of isomerism. For example, Cr NH3 6 times, C2O4 thrice. C2O4 thrice oxalate. This is coordination complex. Here the central metal atom may be exchanged. NH3 6 times, same molecular formula with the exchange of central metal. C2O4 thrice. There is the name also change. Hexaamine chromium 3 trioxalato cobaltate 3. Here it is reverse. Hexamine cobalt 3 trioxalato chromate 3. Exchange of the central metal atom or ion is responsible for such type of isomerism. For example, PT NH3 4 times, CuCl4 can be written as CuNH3 4 times PtCl4. This is coordination isomer. So this completes the first part of isomerism, namely structural isomerism. In the next class, I am going to take up the stereo isomerism. Okay, I will stop here. I will continue in the next class the part of isomerism, namely stereo isomerism. Okay. So I am going to take up this isomerism in the next class, because more and more information for JWE is necessary. I have explained in detail isomerism, EAN and some more IUPAC names of coordination compound. Thank you very much. Now get access to the class practice pack sent by me and try to answer those with a passport. Thank you very much.